Hello, everybody, and welcome to the Taurus Report. I have with me today astrophysicist Lee Greer, who is going to help me go over a few things that have appeared in the news lately that have inspired me to go ahead and do this special episode. Welcome, Lee. Good seeing you again.
Good to see you too, Joe. And again, as mentioned earlier, Happy New Year.
Well, thank you very much. Happy New Year to everybody out there. So, the thing that really interested me and got me started this past week taking a look at this. This is Lee's website. We'll get to that a little later in the show here. Was this article that appeared in the news, Shattering Astrophysical Myths, The Surprising Prevalence of Galactic Winds. And that title is not very revealing to me. Okay, the thing that I found interesting in this article is that, as you know, some time ago in my Taurus report, and as always, I will include all these websites in with the comments when we post the video here. But some time ago in episode 13, I did this one show where I explained how CGC, Cyclic Gravity and Cosmology, interprets black holes such that they are actually neutron stars and actually capable of ejecting matter from their interiors. Now, I explain all the specifics of that in CGC, and I won't go into it any more depth at this point in time. But my point is that, according to CGC, these jets from active galactic nuclei serve to recycle matter in the universe. So, as things get older and more metallic, at some point they have a chance of eventually working their way into the galactic center, and then all of the metals are recycled and spit out again as basic hydrogen or helium. And so I had kind of expressed this several times in presenting CGC, but most specifically in this episode 13. Now, coming back to the article, so this article presents recent research by these scientists, really specifically analyzing these galactic winds, and they're noting that it has this sort of double polar conical shape coming out from the galaxy. Excuse me. And so the thing that I found interesting in the article is their presentation of this conical shape. The article, they seem to attribute all of this matter being ejected to novas and supernovas spread throughout that galaxy, and somehow it is ejected in this sort of conical way, both above the galactic plane and below the galactic plane. But nowhere do they ever explain, why general ejecta from novas spread throughout a galaxy, why it should have this specific dipolar conical shape. And they don't really ever deal with that or explain it. And they certainly don't present it as stemming from the galactic nucleus. And so, Lee, we had discussed earlier about active galactic nuclei, specifically Seyfert galaxies, and also in general quasars, which the two I think are related. And I was hoping that you could, for the audience, just explain a little bit about what quasars are, what Seyfert galaxies are, and kind of the relationship between the two, and what it might possibly have to do with what we're seeing in this article.
Yes, definitely. Well, all galaxies tend to have what is called a galactic nucleus, and there are some galaxies which have a very active galactic nucleus, and they're called AGNs, active galactic nuclei, types of galaxies like that. And some of the most striking examples of this are the Seyfert galaxies, which a surprising number of the common galaxies that someone would see through a telescope, even Messier objects and all of that, meaning they were seen in the 18th century, right? Are Seyfert galaxies, and Seyfert galaxies themselves, they are one of the largest groups of these active galactic nuclei. They have very high surface brightness, a very strong point-like core, in a sense, very high ionization emission lines. They're very striking in appearance, and they tend to have patterns of X-ray and radio emission, even though they are not considered some of the radio loud galaxies.
Right, and I think that the one of the things distinguishing the Seyferts is having this sort of disk, which is,
Yes.
I think, what is the source of the brightness. Is they have this? They're sort of like a quasar. If I understand correctly, a quasar is like what we're seeing here with this disk, but without the disk. In other words, a quasar is ejecting stuff, but we don't see this disk, whereas a Seifert, we kind of see the disk, if I'm understanding it correctly.
Right now, quasars they're extremely luminous, active galactic nuclei. And at first, they were considered to be, when they were first named, and I think the first description of them was published by Martin Schmidt in 1963. They looked like stars, so they were called quasi-stellar objects. Their high redshifts didn't quite make sense. They didn't look like ordinary galaxies, and you really just see this very, very compact, exceedingly luminous core, and often very radio loud. They can also have, like other galactic nuclei, they can have jets on the semi-minor axis, or lobes of emission in X-ray spectrum, X-ray radio spectrum, other areas of the
So,
electromagnetic spectrum.
so
Yeah,
when they were first discovered, people didn't really know exactly what they are. So
exactly,
that's where they got their
exactly,
name, quasi-stellar, meaning we don't really know what this is, kind of.
exactly.
But extremely bright and extremely energetic, and so then slowly over time, then researchers started associating them with galactic nuclei.
Yes, yes. Now, it turns out that, so for instance, Hubble, one of the most famous of these galaxies, is, if I may share a screen for just a second
Sure.
here. Let's see. There we are. Okay. So, one of the most famous of these is, of course, 3C273. Um, and Hubble did this occultation image, so you can see that there is something around the quasar as well. That is images taken some years in the past with what used to be the most magnificent observatory above Earth, which was the
Right,
Hubble
right.
Space Telescope. Of course, now it's been surpassed by the James Webb Space Telescope.
Up here.
By the way, the image of the Seyfert galaxy M82 in that article in Science Daily that you referenced is an absolute magnificent image there. I think it really illustrates the the minor axis cones of emission from the core of the galaxy and all of that.
Right, and for me, one of the things that and I'd kind of like to repeat that, and then we'll get to this other item that we had discussed, is that when we look at the plumes of ejecta,
Yes.
I am confused. Well, I guess I'm not confused. Let me just say out loud just what I'm thinking. Okay, I think
Sure.
standard cosmology, looking at a picture like this, and I'm sorry it's so small here, but where you have this
Well, I
disk.
just shared it large on the screen right now.
Oh yes. Oh, perfect. Okay, good.
Yeah,
Let me
yeah,
just go to that. Let's just go to that. Okay.
sure.
So you have a disk where stuff is infalling into the central core, and
Hmm.
then being ejected in plumes perpendicular to the plane of the galaxy. And I think basically under standard cosmology, of course, if that is a black hole at the center, then according to standard cosmology, nothing at all can ever escape a black hole. And so then,
Right,
according to standard cosmology, basically this stuff is swirling in a disk, and then somehow that swirling motion, uh, as it swirls in, that same stuff, that same matter, would somehow have to be reoriented and ejected out vertically without ever having actually gone to the interior of the black hole
right,
under standard cosmology. Now, of course, under CGC, this stuff could spiral in and hit a certain critical mass because, and when I use the phrase critical mass, what I mean here is that under CGC, neutron stars are only allowed to take certain discrete sizes. And so
right,
if they go beyond that discrete size, then suddenly the surface would become repulsive. And of course, in a black hole or a neutron star, that repulsive force would be proportional with attractive gravitational force at different levels. So it's just another fancy way of me saying it'd be extremely strong repulsive force. And so then under CGC, this stuff would fall in, actually be incorporated into the neutron star. And then at some point, when it hits a critical size, the surface becomes actually repulsive rather than attractive. And then when it becomes repulsive, the stuff would be shot out in this vertical axis. And so also when that is done, the other thing that happens is that things which are metals, if they fell into the neutron star, of course, everything becomes basic neutronium. And so it's
right,
broken down to its constituent nucleons. And so then when things are ejected, there's every possibility it is ejected as fresh hydrogen. And so in this way, everything would be recycled. And in fact, of course, I posit this as a way of justifying a steady state version of the universe, because then if all heavy metals eventually are recycled back into hydrogen, then that cyclic process could go on, of course, indefinitely into the future. And so then we would have a steady state universe, a steady state universe in cosmology where everything is being endlessly recycled like that.
right,
Now, the
right. Well, and of course, with your CGC model, I I think it would be great if we devote a future episodes sometime to some possible very interesting tests that we could have for that cosmology. We have discussed some of those before. I know it's beyond the realm of what we're discussing this episode, but
I think
yeah,
that would be very good. Yes,
yeah,
and the thing that I note is in the some of the items that you sent to me earlier, because I was looking it over this morning, like the Embartsumian. I don't know if I'm pronouncing the names exactly
yes,
correctly.
yeah,
Vorontsov, Veliaminov, and ARP's pioneering work. In those things, as I was looking it over, I came across something in there this morning where one of them, and I'm forgetting off the top of my head right now which one it was, had mentioned that when they're looking at the way galaxies are formed, and they were describing this type of stuff as a mechanism for forming spiral arms. In other words, stuff being shot out far, and then the whole assembly continues to spin and rotate, and you end up with spiral arms. But one of the things one of them said in his paper was that it seems as though there is some sort of repulsive force, and it's difficult to explain all these motions in the absence of a repulsive force.
Yeah,
Which I found very interesting. But as you mentioned some of those researches, uh, I'm wondering if you have any comment on some of that older work
I would love
that
to
you had
do that.
brought up.
Yeah,
Yes,
yeah,
if you
definitely.
could.
So, just while we're on M82, I want to just briefly note a couple things. Notice these terribly explosive strands coming out of the core, and not only just along the major axis, but even to a lesser degree exploding away from the center of this. Now I'm going to show you something very interesting, which was in over the years uh, described. I'm going to share another screen really quick here, and this will be just a second. Here we are, and there. Okay, so here are a couple of galaxies right over on this side. Can you see my cursor? Okay.
Yes, we see your cursor.
Okay.
Yes.
That's M82 here there. And of course here's a Hubble image of it getting close to that. Over the years, it noticed, however, and of course here is a hydrogen alpha image showing this. This is published in 1968. It's interesting how culture affects presentation to the public. So this is a popular book that King wrote in 1968, and exploding galaxies were a matter of topical discussion in 1968. Look at this image. Now, what is very
Interesting.
interesting, here's of course a similar image which we just saw, is that when one looks at it, there are in fact streaming away from that exploding image quasars. Okay, here they are right here that seem to align in ways. And in fact, as more searches have been done, here are the number of quasars. There's a hydrogen alpha cap here, and this is not a random distribution of quasars, which are supposed to be with a higher redshift far in the background. Notice how they align with exploding aspects of this.
Right,
The
they align with that vertical cone
Exactly.
ejecting from the plane of the galaxy. Yes.
Exactly. And then we look at here, this is some of ARP's work. These are many of the objects, including X-ray objects, which are also being emitted from there. In other words, there's stuff pouring out of this galaxy for some reason, and this is one of those Seyfert galaxies. Now, if you don't mind, I'll share another screen because I
Sure.
would like to briefly mention the work of. Well, actually, I can go up the same screen because I want to show you something quite fascinating here. Let me go back to share, and here we are. There. Okay, so this is another one of those active galaxies, NGC 4438. You can see one of those bubbles emerging right out of the core. That's with the wide um, field planetary camera 2 on the Hubble Space Telescope. This is on an unpublished chapter in my website here. And of course, here I discuss some of the issues about the virial theorem. We might touch on that later on. But here is Victor Ambartsumyan, died in 1996. And he said something very interesting in 1961. He had been studying these. He suggested that some galaxy clusters are actually and galaxies are actually or galaxy clusters are actually gravitationally open. They are not bound, so they're coming apart, similar to what we just saw.
Right.
Okay, he says one of the problems confronting us, this is quoting him, in the study of the outflow of matter and ejections from the nuclei of the galaxies is the quantitative evolution of the ejected masses. This refers equally to those galaxies of which the central parts show emission lines, and to the radio galaxies and to other examples with discrete ejections. The few facts at our disposal show that these data may conflict with the law of conservation of energy matter in its present form and may perhaps require a generalization of this law. And of course, in other words, I'm citing in light of the virial theorem that this may not equal zero, but we won't go into
And
that.
that is the derivative of what with respect to time there? The G,
That
what
is
does the G stand for? That is the
the,
gravitational
the
constant or something else?
gravitational the gravitational constant related as it is with the with baryon number, nucleon
Okay.
number.
All
Okay.
right. So
And it's
basically
related
the
it's related to a discussion up here, which is probably beyond the realm of what we need to talk about
right.
right now.
But in essence,
Right.
what it's basically saying, for the layman, is that
Yes,
gravity is not behaving as we would expect. That's basically what it's saying.
exactly. Exactly. Now, of course, then a young astronomer, Halton Art, began looking at at these at a number of these seeming ejecting galaxies, right? And let me just point out one example because there is a recent. Let me zoom down here. There's so much we could say about
Right.
this.
We don't have a lack of topics here, right?
We don't have a lack of topics. So let's just take the example of Seyfert Galaxy NGC 2639, part of the New General Catalog. All right. And years ago, back in 2003, and this was before actually it was published, it was noted that across this galaxy, which is NGC, this Seyfert galaxy, were two quasars of higher redshift. By the way, these are the Z numbers, and are positioned across. So this was a phenomenon which was documented over and over again. Now, in 2019, this paper was published, and this is a paper by Sebastian et al. And there are secondary lobes within there observed at 5 gigahertz in radio and so forth. And the orientation of these lobes, very interestingly, there are secondary lobes and primary lobes. Now, this is interesting before we get into the weeds. There was another paper published. By the way, this is how this galaxy is classified on the Hubble de Vauquelin morphology diagram here. It's an SA galaxy. So it's one of this very tightly wound spiral galaxies. Well, what is observed there is that along the minor axis there are a number of blue stellar objects which are lined up as if they had been ejected, and then here are these two objects here, these quasars right here with the higher Z. It just so happens that the alignment of a primary and secondary jets there, okay, and actually there have been four jet episodes out of the core, and this paper, which is Rao et al. 2023, they of course have tried to attribute it all to naturally accretion disks, right, and mergers, right?
Right.
Okay,
Mergers is a big thing they use all the time.
mergers, yes. Once the fad of quote unquote exploding galaxies were gone, then mergers were in. Correct. And it just so happens that the alignment of two of those lobes, okay, roughly fits with the putatively ejected blue stellar objects and with the quasi-stellar objects
Right,
across
and
that.
then the thing that people kind of criticizing this association would note that the redshift of the quasars according to standard theory, doesn't really match up with the redshift of the source galaxy.
That's right. Well, the odd thing is, and this is again a topic for another time, is that there's an intrinsic component that in the redshift which depends on where you are in the morphology, and that's been known for about 20 years too, but somehow it never makes the discussions. It has been published in the peer-reviewed literature, but it doesn't make the discussions. So in addition to whatever general expansion is happening in the universe, there seem to be intrinsic components to the redshift, and there seem to be these ejecting phenomena. Now let me just quickly wind this up so you can get back on topic. By the way, here's a beautiful image of an ejection. This just happens to be radio and everything for this galaxy here, which is NGC 4258. And wouldn't you know, there are
Quasars directly in that path.
directly. Yes, Margaret Burbage published this years ago at Kitt Peak. Stuff that mergers don't explain this set of phenomena, do they?
No, no, no. You can't explain that with a merger. Yeah,
No,
I mean, I've just noticed the pattern with many things I'm reading now. It's like every time something unusual comes up, you can bet that the word merger is coming in the next paragraph.
right.
So,
So let me show to list some of the papers which are done, and this is already available on the website. I'll go ahead and share this screen here so that you can. So here we are on the home page. If we go to Ambart Sumian, Victor Ambart Sumian, who was actually a very impressive man, a statesman as well as a scientist, one of those complete types of individuals. Okay, and he published more papers. I actually link. There's papers, most of them not translated into English, but these are a series of the papers, and he was exploring this issue. Why do so many? What is the formation of galaxies and galaxy clusters if these galaxy clusters are coming apart rather than assembling? Of course, that raises the issue of dark matter, whether baryonic or not, doesn't it, Joe?
right,
If you
right.
really get down.
Yeah,
And then
if
of course there's a. Go ahead. Sorry.
yeah, if of course, again under CGC, what we would see is things over a period of time going through phases of gentle expansion and contraction. When I mean gentle, I mean if you're talking in terms of huge scales, it would appear as gentle expansion and contraction. Of course, the ejecta are anything but gentle, but on very large scales, things like clusters and galaxies would go through periods of formation and condensation and other periods of disintegration, obviously in a cyclic way. Back and
Yes.
forth, and so, of course, current gravitational theory and the idea of a expansion constant like the Hubble constant that just applies everywhere for all time in an expansive way only would not be able to ever incorporate any such thinking into current cosmology, which if
Absolutely.
if CGC is correct, then of course cosmology would have to go in an entirely different direction.
That's right. Well, there was another Soviet scientist who compiled a catalog, which you can also get for free. I have it linked. It's linked from Caltech, and it's the Vorontsov Velyaminov Atlas and Catalog of Interacting Galaxies, and it in many ways is a precursor of ARP's catalog of peculiar galaxies, and all these amazing unusual galaxies, of which we're finding more as we go further out. You know, uh, there's definitely some interesting phenomena going on which don't nicely fit into the current paradigm,
Right,
which
and with the current paradigm, again, anytime you read about them, we know in the next paragraph the word merger is coming. Whenever something strange or unusual or unexplainable happens, they try to explain it by assuming some sort of collision that did it. Uh,
yes,
so,
and they basically have to, because how else do you derive structure in the hot Big Bang universe, the lambda cold dark matter universe, uh,
right,
you have to assume all of that when the empirical data suggests otherwise. Now, just let me make a quick heretical comment, if I may, because you are proposing a new theory of gravity. When we look at general relativity, which based on the work of was based on the work of many that arose, although it's commonly assigned to Einstein, right? Is that we're thinking of the fact that beyond the Schwarzschild radius, a star that is massive enough, about five solar masses, to where light cannot escape and everything, the gravitational theory of the standard general relativity gravitational theory predicts singularities which are infinite quantities. Now, you also,
as far
as
as
a math,
density, right, infinite density, yeah.
infinite density, correct, which is another way of saying the theory is non-predictive beyond a certain point,
Right,
which
when you get through
suggests
the, yes, that's right,
exactly,
yeah.
which suggests that it may not be a final and complete theory. You know, plus it's been pointed out that that it is not scale invariant. It doesn't engage in the same sort of gauge invariance that we expect of other field theories in modern physics. And so there is something. In other words, there is more to be learned on the gravity front, and I'd say let every model be put out there and tested.
Right.
I think.
Well, I mean, I certainly agree with that. I'm not sure that that's even heretical, Lee.
No, it's not the prevailing paradigm, though, is it? Right.
Right.
So,
Yeah. Well, the big hurdle to get through, and which I attempt to do that in CGC, the largest hurdle is the success of general relativity.
of course,
The biggest success in my view, time dilation and relativistic momentum, being able to predict those two things. Also, the deflection of light. So three
correct,
things,
correct.
and so in those three things, it's highly predictive, very successful, and thus far, people can propose various gravitational theories as I have done, but in general, they don't do any better and usually much worse at dealing with those specific things which are a strength of GR. Now, in CGC, again, this show isn't specifically about that today, so I'm not going to go into it in any great depth. But in CGC, I do provide a mechanism by which those things are accounted for, plus accounting for the types of things like we've been discussing today. When and where and under what circumstances and why we have actual repulsive gravity, and doing away with the idea of singularities at the heart of black holes, which GR predicts. Now, fortunately for GR, making such a prediction at the heart of a black hole is something that obviously cannot be confirmed. So there's no way to go to the center of a black hole and say, okay, do we actually have a singularity here or not? There's no way to do that. So in the areas where general relativity is, in my opinion, weakest, in those areas they're not really testable. And so general relativity is basically safe from criticism on that front until we can figure out some way of actually testing that. So,
Right, right, right. So if we're so let's just say, for instance, if there's a I'm going to share my screen just one second further here, if that's okay.
sure.
There we are. So if we consider Ernst Mach here, this this very fascinating gentleman. Of course, I give a little history of the view of the idea of inertia, and Ernst Mach made he followed up on Newton's bucket experiment where water's spinning in a dish, and actually this has been done. It forms this lovely paraboloid surface here.
As it's
Uh,
spinning in a dish, yes.
exactly, exactly, and and it can be described by some fairly straightforward math. The big question was in reference to what does Newton's bucket and its contents, or it can be Foucault's gyroscope and his pendulum also. Um, what is it with reference to what is it spinning? Of course, Newton said with reference to an ideal inertial frame of absolute space, right? Okay. And general relativity actually is a modification of of that idea. It's still in essence within the framework of, even though Einstein sought to follow Mach's principle, he didn't really succeed. It's in reference to the relativistic inertial frame of the system. All right. But Mach said basically that it's with reference to the relative distribution of masses throughout the universe out there. Now, I think that whether it's CGC or whatever model turns out to be true, I believe it will have to abide by Mach's principle, in that all of the motions and gravity and inertia and redshifts and whatever is going on will have to be referenced to the distribution of inertial systems throughout the universe, not to any arbitrary framework, whether Newtonian or general
I
relativistic.
agree with that. Yes, certainly. I think that I describe time as the record of change, and then that begs the question: the record of change of what? And to me, that is what matter and energy is the potential for various types of change. And
Right,
so all matter and energy together would constitute what we call the universe.
right,
And I think that the basic conservation law is just absolutely correct. It can be neither created nor destroyed. There is some total, and whatever calculations we're doing, whether we're talking about motion or we're talking about the change of form of energy, or and whether the motion is linear or rotational. All of those things, to me, and it's sort of a common sense-ish thing, they're conserved. That seems sort of common sense to me, and I think that in this context, the common sense is correct. So the idea of energy being created and injected steadily into the universe, as in, the current formulation of dark energy, and just in general, the idea of a Big Bang where cosmological history is linear like that, like it started at some dense hot point and we're going to some uh, loose, non-dense, cool point in the future, or if the energy density is staying constant by injecting new energy constantly into the universe, as dark energy does. I think in a common sense sort of way that's ridiculous. And so I am definitely a subscriber to what Mach was saying, where when the proper way of relating any specific environment to the universe would be to relate to the universe in theory as a whole. You're relating to the sum of everything, and so of course, as finite beings, we have to make simplifying assumptions because
Of course.
we can't really account for everything in the universe when we're doing our calculations. But that's why I say, in theory, it must be related to all of that. But yes, in that sense, I'm definitely Machian myself.
Yes. Well, and it is possible that some formalism may be found at some point, which can easily, or in a straightforward manner, solve that without you having to know where every
Right.
mass is in the universe. I mean, let's put it this way. You know, the one of the founding algebraists of modern physics, of course, is is Amelia Noether, who enunciated her famous principle that for every law of conservation there is a corresponding symmetry, and for every symmetry there is a corresponding law of conservation. You know,
Mm-hmm.
um, that may be true at a deeper sense than we think right now at certain energy levels, such that overall conservation is preserved, but baryonic conservation may not be preserved. Now, the Big Bang already has to assume that that's the case in an inflationary scenario, that somewhere between the bang and the end of inflation, it isn't conserved. But that's an irreproducible situation with, as we talked about last time, whatever 28 orders of drop in temperature, supercooling, and all that kind
Right.
of
Well,
business.
that's one of the inelegant or unattractive things about standard theory is, of course, as we discuss many times, is you have when we're talking about basic conservation laws and basic assumptions, we make assumptions based on what we're seeing all around us. And so we kind of assume what we're looking at to be sort of universal. Um, but standard cosmology, while claiming to do that, really does not do that because it's always positing these things such as the Big Bang, such as inflation, such as dark energy, such as dark matter, all sorts of things which are not observed at all and are purely hypothetical. And although they are unobserved and hypothetical, they are foundational to standard cosmology, which to a layman,
Epicycles.
to a layman, it just seems absurd in one sense. In one sense, I understand it perfectly. Epicycle is a very good example. People used epicycles for a reason. It worked. I mean,
Yes,
for a
right.
thousand years, the Ptolemaic system was highly predictive. It was excellent. It did better than anybody else could do. It made very good predictions. And so you had to assume these celestial spheres, and then you had to assume mini spheres within those spheres, and then other spheres within those spheres. And you're assuming all these transparent spheres out there. And I'm sure there were many thinkers who thought, well, I don't really believe all those transparent spheres are out there, but the math works out. We're able to make predictions. And so when a standard
Right.
modern cosmologist says we assume all these things in order to make our predictions, and GRLCDM, hot Big Bang, although it fails in some things, it does succeed in a lot of other things. Okay, and so
Correct. Yep.
as long as it helps you to make predictions, then it's understandable that it be used. Um, where I start having a problem is when people start actually, you know, rather than just simply acknowledge that it's a mathematical crutch,
Right.
if they actually believe in something like inflation, it just seems to me ridiculous. It's like, okay, I understand the math why you're doing it, but obviously the idea of the universe expanding at that rate is pretty ridiculous, absent observation. You know. So, anyways, that's my pontificating on that topic. So,
Yeah, yeah. Well, it is interesting. We should note that standard cosmology has some very um, well placed challengers.
well, thank you very much, Lee, for your comments. Thank you for coming on the show. Again, Happy New Year to you and to everyone else watching. I would like to refer everybody to Lee's site, enlightenmentlegacy.net. I will include the links to his site in the comments for the video. So, thank you all very much for joining us today at the Taurus Report, and we will see you again soon. Bye bye for now.